Hello everyone. I'm gonna do some HNMR right up here on the board. As always, encourage you to try it on your own first, and then go back and we'll walk through it. This is gonna be on the ACS, and you should be expected to know also where certain functional groups should lie with regards to hydrogens surrounding them. So with that, probably going to be about 15 or 20 numbers you have to remember for combination for both hydrogen and carbon spec. So there's probably Quizlets out there. I might just make one. It should only take a couple minutes of functional groups, common functional groups like ketone, yep, alkene and alcohol, and aldehyde, just for examples. So the first HNMR video I did, I was able to do everything. I was able to look at, the intensity, the splitting, and the different number of different hydrogen groups. I was able to do all of that, but I wasn't able to really put it and orient it on the spec. So now I can be able to, I'm gonna have to use my phone to see where these are gonna lie, but you should have them memorized before you take the ACS. Probably about 8 functional groups, and then 8 for HNMR and 8 for C. So I'm going to start the same way, and the last thing I'm going to do is put it actually oriented on my what I made here. HNMR goes from like 1 to 12. CNMR goes up to beyond 100. I can't quite remember. All right, first step, we're going to identify unique hydrogen groups. I have a symmetrical molecule here, so these 3 hydrogens are the same as these 3 over here. Carbon, carbon, carbonyl. Carbon, carbon, carbonyl. It's symmetrical right down the middle. Should have those 6 hydrogens there are all going to be the same. And then these 2 hydrogens and these 2 will be the same. With more practice, you'll be able to see that right away. Lines of symmetry, okay? So I only should expect to have, in my HNMR, 2 peaks. Now those peaks might split and they might be different intensities, and they're gonna also vary in orientation, but I should expect 2 groups. Intensity with HNMR lines up perfectly with how many hydrogens we have. So we have 6 red to 4 blue. So we should expect on a 3:2 ratio, or 6:4, our red peak to be, 50% taller. We can also look at splitting. Let me write intensity here, and I'll write splitting right below it. Splitting, remember, you look at beta hydrogens. So how many beta hydrogens are there for each group? I can choose one of my red groups. I'll choose this one here. How many beta hydrogens do I have? 2. 2 plus 1, remember when we split, we just add 1. So I have 2 beta hydrogens, I add 1. This should be split into 3 groups. Intensity of 6, split into 3. And I can choose my blue group. How many beta hydrogens do I have? None here with the ketone, 3 here to the right, 3 plus 1, this should be split into 4 groups. All right, cool. Now, all of these hydrogens are on an alkane. Now, the blue group being closer to the ketone, it's probably gonna make it a little bit different, but for ACS terms, it shouldn't. All alkanes or alkyl groups should lie between 1 and 2. So all alkane hydrogens, if it's just on an alkane, should lie between 1 and 2. Right around 1 is primary, right around 1.5, secondary, and right around 2 is tertiary. So there's not a lot of room there. But if I have a primary, which would be this right here, primary carbon with 3 hydrogens, that's going to be right around 1. And then if I had, let's say, a species there with a tertiary carbon with 1 hydrogen, that would be tertiary, that's going to be around 2. They're all going to be really close to each other, really. All of your alkanes are going to be all the way on the right side. So first, I need to draw intensity of 6, split into 3, and it's in a primary carbon, that's going to be right around number 1. So intensity of 6 at number 1, we'll say that's 6 tall. It's all relative. Split into 3. So something like that. You might also see it probably more so like, this is a lot easier to draw, but something like where that's 1 signal and they'll be really close together. But this is good for our use here. Intensity of 6, split into 3 at this position because it's a primary carbon. And where it lies here, again, depends on the functional group. You will have those memorized. You should not be expected to know that right now. I'll go to the blue carbon. I need intensity of 4, split into 4, and it's on a secondary, so it's going to be just a little bit left, a little bit further upstream on our spec. So intensity of 4, so about 2/3 of our red line, and split into 4. So something kind of like that. Because we only have alkane hydrogens, our spec's going to be loaded at the very early part. All of this over here is when you get in other functional groups. We'll get into that in the next 2 examples. But if I just have alkyl hydrogens, expect your right side of your spec to be loaded. There you go. Let's keep it moving. Red example here of an alkene and an alcohol, both of which will have their own spot down here, which I don't know because I don't have it memorized, but I have my phone on me to check. Let's start. I don't have or shouldn't expect any symmetry in this molecule, so we're going to expect a lot of signals. Notice each group of hydrogens should be chemically different. We'll first start with a methyl group all the way over here. 3 hydrogens there. I have one on my alkene here. One on my alkene over here. Okay, these are both alkene hydrogens. Why are they different? It's because this side of our alkene is different than that side of our alkene. You know, that's going to influence, that's going to make the chemical environment of which these hydrogens are at different. So we have another hydrogen right that's a highlighter. Right here. Another methyl group up top. And then our red alcohol hydrogen right there. So we have 1, 2, 3, 4, 5, 6 distinct groups. We should expect 6 different signals in our spec. Okay. Black hydrogens on the left. We have 3 of them. So intensity, and I'm going to call this group 1. So intensity, let's just call this group 1, and we'll say 3. Hydrogen here, we'll call group 2, intensity 1. Purple group, there's 1 hydrogen, our intensity 1. black hydrogen here, intensity 1. And we'll call that 4. It'd be easier if I had more markers. I'll call this 3. Number 4, intensity 1. 5, intensity 3. Because there's 3 hydrogens. And lastly, intensity of 1 on our alcohol, which we'll call 6. Okay, that looks ugly. Let's look at now splitting. Splitting with group 1, 2, blue. I don't know why I'm drawing the numbers again. I should not do that. It's already in a graph. All right, black hydrogens. How many beta carbons do we have? Correct, just 1. 1 plus 1, split into 2. Blue carbon, how many beta hydrogens do we have? Correct, 4. 1, 2, 3, 4. 4 plus 1, split into 5. Purple carbon, or purple hydrogen, how many beta carbons do I have? 1, or hydrogens, excuse me. 1 on the left, and then 1 on the right. 2 plus 1, 3, split into 3 groups. How many beta hydrogens here? I have 1, 2, 3, 4. This one here, not probably going to count. If it comes down to that, it won't come down to that. That's not going to make or break it on a multiple choice spec, but from my understanding, it should only be beta hydrogens relative to, like in a carbon, bonded to a beta carbon. So we're going to say in our purpose, and again, this is not going to make or break, you'll still get it right if you've gone this far, and you'll probably, it's probably going to get to the point where you can just look at it and hopefully fill in the bubble. Anyway, beta carbon to the left, 1 hydrogen, beta carbon above, 3, 4 beta hydrogens plus 1 split into 5. Blue position, I have 1 beta hydrogen, 1 plus 1 split into 2. And lastly, our red should just be a single signal. Yeah, should just be a single signal. Okay, so now we know how intense each signal is, how much it's split into. Now we have to find where they're going to lie. So our first one, you should know where it lies. I have an alkyl group, okay? Methyl group, so primary alkyl group. This should be all the way on number 1. So let's start with that. Intensity of 3, split into 2 on position 1. Intensity of 3, split into 2 on position 1. And again, the intensity is all relative. I could have written intensity over here, but it's relative. Next, we have intensity of 1, split into 5, so a short, fat signal on an alkene. Alkenes, they are going to be oh, you know what? Do they have, they do, okay. I'm going to take this signal and I'm going to move it over a little bit because that's not necessarily primary position. I screwed up. What position is this more correctly? This is the allylic position. Okay, so let's add allylic to our chart. That's going to be a little upstream. Allylic is going to be right around 2. So right around tertiary. So about tertiary, when we talk about stability with radicals and carbocations, we usually put tertiary and allylic pretty close to each other. Same spec. Allylic's going to be right around here too. And I added an L, just for safe measure. So intensity of 3, split into 2 at our allylic position. Allylic hydrogen is there. Here we have a vinylic hydrogen, it's on the double bond. Those are going to be, let's see, right around 5, maybe just above 5. So vinylic hydrogens, intensity of 1, split into 5, so about a third as tall, 5 signals like that. There we go. This is overkill, big time for ACS. But you got this, you'll be fine on the test, okay? Overkill to an extreme. But it's good practice. Next, let's look at purple. Purple is also vinylic, and that's it. So right around, and this is where we kind of get into that gray area. You'll probably have multiple signals showing up. So ACS, they're gonna avoid that. In real life, it gets messy, and they overlap, and they interfere with each other. So we're gonna draw it probably over top of number 5, but considering it's closer to the alcohol and it has more alkyl groups on it or near it, it's probably gonna shift it one way or the other. But we don't really know which way, at least I'm not sure. Anyway, we have another vinylic, so we're gonna stick at this position. Same intensity, only split into 3. I'm just gonna write it above it. Okay, that's not what happens in real life, but I'll put some parentheses here, and in the same spot we should expect something like that. I'll put in parentheses. Tough to really see, I understand. This is, I don't need this again. Okay. But this is 3 signals and intensity of 1. Group number 4, hydrogen. Allylic position. Notice, allylic position, 1 away from a double bond. So again, we're gonna get some overlap. Intensity of 1 split into 5. Right around this area, we should also expect a short signal like this. Intensity of 1, split into 5, in the allylic position. Clearly, I did not design these in a great way. I just wrote them up there. And if you notice, they all have the same chemical formula. C5H10O. So that's good, but what I didn't account for is these overlapping spec. But these, take this down here in real life and it's gonna kind of merge. Muddy the waters. 5 is gonna be, well, we just have an alkyl group there, intensity of 3, split into 2. And since it's just a regular primary alkane, it's gonna be right around number 1, intensity of 3. I said this one was 3, so I'm gonna make it as tall. Split into 2. There you go. And last group, our alcohol. Intensity of 1, not split. Alcohols are okay. Bad news. Bad news. Alcohols can be anywhere from 0.5 to 5. So you get to choose. I don't know. Of course, 0 to 5 is depending on the surrounding environment. We can't know that, and alcohols aren't going to really tell us that much. So are they going to be on the ACS? Probably not. But for our purpose, we're just going to split the middle. We'll say it's around 3. Intensity of 1, split into 1. There's our spec for that one. 1, 2, 3, 4, 5, 6 signals because we had 6 distinct, chemically distinct hydrogen groups. We determined intensity based on the number of hydrogens in each group. And we determined splitting based on the number of beta hydrogens relative to each group. Lastly, we determined position based on memorization and the Quizlet that you'll have to memorize before you take the ACS. Last example here, we have an aldehyde. And I mean, okay, looking at my phone, aldehydes are around a 10. Aldehydes are around a 10. I should expect, I can see right now, 1, 2, 3, 4. I should expect 5 different signals. They're all different. There's no symmetry there. I should expect 5 different signals. And yeah, I'll keep it this way. Those 4 alkane groups, they're going to be way over here on my spec. I should know that. They're all alkanes. They're going to be between 1, 1, and 2. So I should expect 4 small, probably heavily split because there's lots of beta hydrogens over here. And I should expect my aldehyde to be about a 10. So I should have 1 peak way over here on 10, indicative of an aldehyde, and 4 smaller, well, they'll be intensity, but they'll be split a lot because a lot of beta hydrogens. Experience with, I can look at that and I can probably circle an answer at this point. Just because I'm used to doing spec, I can see aldehydes way over here on 10, there's 1 signal. All these are going to be low or high signals, but stumpy. So that's my prediction. Let's see if I'm correct. I should expect intense split signals over here and 1 signal right there. All right. Here's 3 hydrogens that are the same. Here's 2 hydrogens that are the same. And we'll call those H1. Here's 2 hydrogens that are the same. Different environment. There are 2 hydrogens up there. Here's 2 hydrogens that are the same. And we'll call these all H1s over here as well. So black H1s, blue H1s. And then we use blue. My aldehyde, hydrogen not drawn in. The numbers are just because I have to reuse the same colors. So black 1's over here, black 2's there, blue 1's, blue 2 of my aldehyde. All right. Did I draw it? Let's start with intensity. Intensity is easy. H1s, those are going to be 3, intensity of 3. Blue H1s, intensity of 2, because there's 2 of them. Same with the red, there's 2 hydrogens there, so red hydrogen is going to be 2. Black H2, intensity of 2. And lastly with the aldehyde, I just have 1, so intensity of 1. It might vary, but it should be an intensity of 1, considering there's only 1 of them. Probably. Intensity is easy, let's do splitting. Splitting. How many beta hydrogens do we have? Our first group, how many beta hydrogens do we have? 2, 2, plus 1, because that's what we do when we split. 3 groups. Blue, how many beta hydrogens do we have? Beta position, 1, 2, 3. Beta position, 4, 5. 5 beta hydrogens, plus 1. Expect that one to split into 6. How many beta hydrogens for our red? 1, 2, 3, 4. 4 plus 1 is 5. Expect this one to split into 5. How many should this split into? Beta 1, 2, beta 3. So that will be 3 plus 1 split into 4. That is carbon. And is the aldehyde going to split? Let's say so. I mean, yeah. So beta position here, the carbon. Oh no. There's no beta hydrogens on that one. So no, there is. Excuse me. Hydrogen here, alpha position, beta. I have 2 hydrogens there. 2 plus 1. Expect that one to split into 3. Okay. I have primary alkane group there, primary alkyl group. So that's going to be right at about 1, intensity of 3, split into 3. Location 1, intensity of 3, split into 3. Next I have a secondary alkane group. Split into 6, intensity of 2. Intensity of 2, split into 6. And also in this area, I'll have my red, because it's also a secondary, and this should be right around 1.5. This should be right around in this area here. All of these 3 groups are all going to be in the same spot. Again, it's overkill. They'll design it in a way to where it does not overlap like this, but it's just extra practice. So we'd expect this to be in about the same spot, intensity of 2. Intensity of 2, split into 5. The same spot as our blue. And our H2. Intensity of 2, split into 4 at the same location. Intensity of 2, split into 4 at about the same location. So all those are going to be overlapping right around this star right here, right about 1.5. That's where our secondary groups go. My prediction so far is correct. I have heavily split signals of high intensity all clustered right at the beginning. I last predicted that there would be 1 signal indicative of our aldehyde all the way around 10. We have that. Intensity of 1 split into 3. Aldehydes are right around 10, so right there. And there we go. 3 different specs, all for the same chemical formula, but by rearranging where the bonds are, I can make different functional groups, and we use spec to really identify what we're working with. We can be provided only this and say, oh geez, I have a lot of alkane groups, and then oh, I have 1 functional group. I look at my chart, probably an aldehyde. And then you can use the splitting to help you out even further and predict molecule, which you did in lab. If you didn't do that in lab, sorry, this is what you have only. That's disappointing. Disappointing that I have to teach it to you, because, yeah. HNMR, just going to be memorization, because there's no splitting, there's no intensity, just no functional groups. I might make a Quizlet. There's probably already Quizlets made. Maybe I can just use those for knowing what these functional groups are. For example, aldehyde's going to be at 10. That's nice to know. So none of this you'll be assessed on, but it should show up in ACS, and well, it will show up in ACS. So help you get to that 70% threshold. That's probably long enough video, definitely. Still shorter than SI, so you're welcome for that. And I will see you all in class tomorrow, but also SI next week, Monday through Thursday. It's a lot of fun.